M.S. Ramaiah University of Applied Sciences.
Hello students, let us know about Pental turbine. Flowing water possesses energy, and this is beautifully displayed in the form of waterfalls. The energy from the waterfalls can be converted to electricity, which improves quality of human life. The safe use of high-grade energy like electricity improves the standard of living and general well-being. Alternate to a natural waterfalls, dams can be constructed in suitable geographic locations and power from stored water in the reservoir can be tapped. Fluid energy has three parts to it: potential energy, kinetic energy, and pressure. Energy conversion from potential energy of falling water to mechanical rotational work is the principle of hydroelectric power conversion. The energy conversion is accomplished using devices called hydraulic turbines. Hydraulic turbines comes in various sizes and shapes and can be broadly classified as impulse and reaction turbines according to the type of energy conversion. An impulse turbine first converts the water inlet head into a high velocity jet. This jet strikes the buckets on the runner at the same spot. Example is the Pental wheel turbine. In an impulse turbine, the pressure of water at inlet, turbine blades and outlet is at atmospheric pressure. A reaction turbine has fluid passages in its runner that converts both the fluid inlet head and pressure into mechanical work. Examples includes Francis turbine and Kaplan turbine. In a reaction turbine, the pressure decreases as the water passes from the inlet section through the turbine and at the exit of turbine. According to the direction of flow, hydraulic turbines can be classified as tangential flow turbines like the Pental wheel turbine for high head applications, radial flow turbines such as Fournier turbine, axial flow turbines, for example, Kaplan turbine used in low head applications. Mixed flow turbines, common example is a Francis turbine for medium head situations. According to the water inlet condition, high head turbine, for example, Pental wheel. Medium head turbine, for example, Francis turbine. Low head turbine, for example, Kaplan turbine. A Francis turbine is a medium head reaction turbine. It is a mixed flow turbine. A Kaplan turbine is a low head axial flow reaction turbine. A Pental wheel is an impulse turbine with high head and tangential flow. Pental wheel turbine is specifically the only tangential flow turbine. It is used when a high head of water is available and is an impulse turbine. The pressure of water remains at atmospheric throughout the energy conversion process and avoids the use of draft tube at the exit. The main components of Pental wheel turbine are the buckets, runner, nozzle with spare valve, braking jet, casing, shaft with bearing, etc. In a Pental wheel setup, the water from the reservoir descends through penstock and the potential energy of water is converted into kinetic energy. Further, there is a nozzle that produces a high velocity jet that impinges the bucket. The nozzle is fitted with spare valve to regulate the flow rate of jet. Braking jets are also provided to help in reducing the speed of the runner during the stopping of the turbine for maintenance. The bucket geometry is double cusped, shaped with a central rib design. The outer tip of the bucket is notched to allow the jet of water to hit multiple buckets. The water hits the central rib of the bucket and is split into two parts, which nullifies the axial forces. Runner is a device analogous to an impeller in a centrifugal pump. It is a combination of buckets on the perimeter of a disc. Runner is connected to the shaft at the center. The casing is a cover for the runner assembly, which just stops the splashing of water. The pressure inside the casing of an impulse turbine is equal to ambient conditions. It can be shown that the maximum power output is obtained when the bucket velocity is half the jet velocity. The specific speed value for a turbine is a speed of a geometrically similar turbine which would produce unit rotational speed under same conditions. The equation for the specific speed is given as Ns is equal to N square root of P by h to the power 5 by 2. With this calculation, we can compare the different turbines. Pental wheel is a low specific speed turbine. Francis turbine is a medium specific speed turbine. And Kaplan is a high specific speed turbine. Pental wheel is a high head turbine. Francis turbine is a medium head turbine. And Kaplan turbine is a low head turbine. On similar scales as the specific speed, unit quantities also can be calculated. Unit power is defined as a power developed by a turbine working under a unit head and is given by Pu is equal to P by h to the power 3 by 2. Unit discharge is defined as the discharge passing through a turbine which is working under a unit head, which is given as Qu is equal to Q by h. Unit speed is defined as the speed of a turbine working under a unit head and can be calculated as Nu is equal to N by h. Plotting the main characteristic graphs, that is constant head graphs, using unit quantities helps us to scale the turbine. It gives a deeper understanding about the turbine performance. At MSR UAS laboratories, there is a setup of combined Pental wheel and multi-stage centrifugal pump. The high head for the turbine is made available through the delivery of the multi-stage centrifugal pump at high pressure. The experiment on Pental wheel can be conducted in two different modes, either by keeping the head constant or by keeping the speed constant for different valve openings and loads.
Hello everyone, this is the setup at our turbo machinery lab to calculate the efficiency of a Pental wheel turbine. The setup of a turbine consists of a storage tank where the water is being stored. This water is being pumped through the centrifugal pump, and the outlet of the pump is connected to a venturi meter. Here we use the venturi meter to calculate the discharge of the fluid through the pipe. This is the inlet section of the venturi and this is the throat section. The water further is connected to a spear head valve. By rotating the wheel of the valve, we can either close or open the valve. The shaft of the Pental wheel is connected to a brake drum dynamometer. So the rope which is present on the brake drum as a friction will add the load on the turbine. The load can be indicated on the mechanical balance. There are two balances, one at this end and one at the opposite end of the dynamometer. The difference in the forces will be the net force acting on the Pental wheel, and this force can be used to measure the torque that is being applied on the shaft. The load on the brake drum can be applied by rotating this wheel. By doing so, the rope can be actually tightened on the brake drum, which acts as a load on the shaft. This is the panel for the Pental wheel setup, which is used to indicate the pressures and the speed of the Pental wheel. The inlet pressure of the venturi meter is indicated in this dial gauge. The throat pressure is indicated in this dial gauge. Both the pressures are in terms of kg per centimeter square. The speed of the Pental wheel is indicated in this LED indicator. To ensure that the speed is being shown, we have to shift the toggle switch to the right. Now, before starting the experiment, we have to ensure that the multi-stage centrifugal pump is completely primed and the delivery valve has to be completely open. Also, we must ensure that the bypass valve should be completely closed and the spearhead valve at the inlet of the Pental wheel is to be completely open. The main switch of the MCB is to be turned on such that all the three indications on the bulb is to be glown, and then we start the pump. Completely open, and we can see that the venturi inlet pressure is showing a value of 1.8 kg per centimeter square. Also, the throat pressure showing a value of around 1.3 kg per centimeter square. Using these values, we can calculate the discharge of the fluid through the line, and also we have to maintain the inlet head to the Pental wheel. We shall now apply the load on the brake drum by rotating this wheel. I have applied a force of 2.5 kg on this end. On the other end, the value of the force is about 0.75 kg. The difference between 2.5 and 0.75 will give the net force being acted on the Pental wheel shaft. The speed of the Pental wheel is being indicated over here. The speed is around 990 revolutions per minute. Now, after the trial 1 is completed, we take the trial 2 by closing or opening the valve. Right now it was fully open, and now I shall close it by 25%. conducting the experiment at constant head, we need to maintain the same head for all the trials. In trial 1, the inlet pressure was indicating 1.8 kg per centimeter square. In order to reduce the pressure from about 2.6 back to 1.8, we have to open the bypass valve. By opening the bypass valve, we divert the flow back to the storage tank, and thereby reducing the inlet pressure to the turbine. Now we can observe that for trial number 2, the inlet pressure is about 1.8 kg per centimeter square. Now the values of inlet pressure, throat pressure and the value of the speed of the Pental wheel has to be noted down for each and every trial. But we have to ensure that the inlet pressure to the Pental wheel is maintained at constant head for every trial. In order to do so, we have to open the bypass valve such that at the inlet we have the constant head for every trial. Thus, by doing, we can do the analysis for the Pental wheel at constant head. Now, after the trials have been completed, we can repeat the same experiments by maintaining constant speed. In order to do that, we now maintain same speed for every trial by again operating the bypass valve. For every trial, we can increase or decrease the load on the brake drum. Thereby, we can have different number of readings at different loads, and also we can do that for constant head as well as for constant speed.
At MSR UAS, we spark your imagination unlike any other.